Welcome to this explainer. Okay, so we all know electricity basically powers our entire lives, right? But today, we're diving into the actual invisible architecture of it all, the staggering subatomic math, and the really elegant physical rules that make DC circuits function.
Here's our roadmap for today. We're going to hit the fundamentals of electrical quantities, resistance and Ohm's law, explore series circuits, understand parallel circuits, and then finish up with a series versus parallel showdown.
All right, kicking things off with Section 1, Fundamentals of Electrical Quantities.
So, before we even touch a wire or build a circuit, we kind of have to ask, what exactly is an electric current? I mean, we know current flows when you plug your phone in, but what is literally moving around inside that cable?
Well, according to modern electron theory, it all comes down to atoms. Specifically, it's a deficit or an excess of revolving electrons. When those tiny atoms get imbalanced, bam, it creates an electrical charge. That invisible subatomic shuffle, that is the absolute core of all electrical power.
And to really grasp this, you've got to appreciate the mind-boggling scale we're talking about here. One single coulomb of charge equals the charge of 6.28 times 10 to the 18th power electrons. That is billions upon billions of microscopic particles moving just to give you one single unit of charge. Absolutely wild.
So, how do we get them moving? Step 1. We apply a potential difference, which is just what we commonly call voltage. This acts like a massive subatomic shove. Step 2. That shove forces those billions of free electrons to overcome atomic collisions, pushing them from one atom to the next. And finally, Step 3. That continuous flow gives us our conventional current.
Moving right along to Section 2, Resistance and Ohm's Law. Discovered by George Simon Ohm, this vital formula, V equals I times R, is basically the bedrock of circuit theory. It proves that voltage, or V, is simply the electric current I multiplied by the resistance it faces, R. Think of it exactly like water flowing through a pipe. The pressure is your voltage, the actual water flowing is the current, and how narrow that pipe is, well, that's your resistance.
But that brings up a really crucial question. Is this golden rule truly universal? Like, is V equals I times R an unbreakable law of physics no matter what material or conditions you're dealing with in engineering?
Surprisingly, no, it's not. Ohm's law actually falls apart under a few specific conditions. For instance, if you drastically change the temperature of your conductor, that nice, clean, linear relationship just shatters. It also fails if you're using specific non-metallic conductors like silicon carbide or non-linear devices like Zener diodes. So it's an incredibly useful law, for sure, but you really have to know its limits. Now, to put resistance into perspective, get a load of this incredibly tiny number. 1.738 times 10 to the negative 8th ohmmeters. That is the actual calculated specific resistance, or resistivity, for a solid piece of copper wire. It mathematically proves exactly why copper is the undisputed king of wiring. Its natural resistance to electron flow is just almost non-existent.
All right, let's see how we actually wire these things up. Section 3, Exploring Series Circuits.
A series circuit is essentially a one-lane highway. Imagine a 200-volt source pushing current through three distinct resistors, say 30, 25, and 40 ohms, all stacked in a single line. There is only one continuous path for those electrons to travel from the positive terminal all the way back around to the negative one.
And because that current literally has nowhere else to go, step 1, it stays perfectly constant through every single element. It's exactly the same throughout. But step 2, the voltage gets chopped up and distributed across each individual resistor. The really cool part is step 3. If you add up all those individual voltage drops, they will perfectly equal your total starting voltage.
But as you might guess, there's a pretty fatal flaw to this one-lane design. If you've ever spent hours, and I mean literally hours, trying to find the one broken bulb in a string of holiday lights, you already know the pain. A single break stops all flow and renders the entire circuit completely dead. Plus, because different devices need different voltages, wiring your entire house in series would be an absolute disaster.
So, how do we fix the one-lane problem? Section 4, Understanding Parallel Circuits.
We fix it by splitting the flow. By creating multiple branches, the total equivalent resistance of the entire circuit actually drops. It uses a reciprocal formula to figure this out. You can think of it kind of like opening up more checkout lanes at a grocery store. Even if there are more people overall, adding those extra lanes decreases the overall friction, letting traffic flow much faster.
And this is the absolute magic behind your home's wiring. In parallel, the voltage is the exact same across all elements, while the currents adjust themselves individually for each branch. And the best part? A break in one branch doesn't affect the others at all. You can turn off your TV without plunging your whole living room into total darkness. Let's bring it all together for the grand finale. Section 5, Series versus Parallel Comparison.
Think about how completely opposite these two math formulas are. When you add a component in a series circuit, your total resistance steadily adds up and increases. But add a component in parallel, and the overall circuit resistance actually shrinks. It's a fascinating mathematical quirk, and it literally dictates the entire architecture of our modern world.
It really all comes down to an elegant physical symmetry. In series, your current is the same through all elements, but your voltage is distributed. In parallel, it flips completely. Voltage is the same across each element, and the current is divided across the branches. It's a perfect inverse behavior, based entirely on whether those invisible electrons have just one path or multiple paths.
So the next time you switch on a single light bulb without magically killing your fridge, your microwave, and your internet router all at once, ask yourself just how many parallel paths are working invisibly behind your walls right now. And honestly, what happens to that incredibly delicate electrical balance when we keep adding more and more devices to the grid? Something to think about. Thanks for joining me for this explainer, and I'll catch you next time.